Thank you. Thank you, Uli, and thanks to all the organizers for inviting me. Really happy to speak at my first ISOL conference, and to everyone who stayed up this late to hear. A quick plug for the Gordon Research Conference in January that I'm chairing, and vice chair is Laurie Barge. Normally this conference is held in Galveston, but they've moved it to California, Southern California in the winter. It's fantastic, because Texas does not allow for mandated vaccinations and masks, which the GRC is requiring. So hope to see you all there in person. So we wrote a paper in 2014 that basically recognized the fact that there's all kinds of different molecules in the environment, and the origin of life probably required coevolution and mutualism between these different types of molecules. And so the question that I want to ask today is to ask, is this actually quote unquote feasible, i.e. Experimentally demonstrable? I mean, it's feasible, obviously, that's how we're sitting here in real life, but can we show this in the lab? So we have taken a shot at this in over a period of many years. And what I would like to show you today is my perspective on how minerals and metals may have played a role in helping biomolecules evolve. And I will give you 3 short stories here. First, we'll talk about how photocatalytic minerals that were close to the protocell membrane may have helped do a transmembrane electron transfer reaction, do the NAD plus to NADH reduction inside the cell, and create protons outside the cell so that you get a transmembrane electron gradient. Sorry. I guess my mouse is jumping around. The other story I would like to say then is, well, could these minerals, when in contact with the mineral surface, could they, with the cell surface, could they potentially have disrupted the membrane or promoted its formation? And also metal ions like magnesium and calcium, which are traditionally thought to be deleterious to protocell fatty acid-based membranes, what might their role have been in membrane stability and evolution? And finally, we would look at the role of clay minerals in RNA polymerization, especially in regards to the role of co-evolution with amino acids and ions like magnesium, which are usually thought to be essential for RNA polymerization. So when I say here E1, E2, E3, what I mean is normally there are enzymes that biologically do these things. And we're interested in seeing whether minerals could have played effective roles, which as proto-metabolic enzymes. And we don't have time to get to this, so we're gonna not get there today. All right, so the first step is, can minerals promote proto-metabolism? So we make a synthetic cell of either fatty acid or phospholipid, and encapsulate within it an electron mediator, rhodium tris-bipyridinium, a cofactor NAD+, and add photocatalytic minerals of different kinds, pyrite, cadmium sulfide, titania, zinc oxide, shine UV light. That generates an electron in a hole. The hole is picked up by any reduced organic compound. We've used a bunch of different amino acids, different kinds of organic molecules. That hole then oxidizes that, and in the process, protons are released outside the membranes. Meanwhile, the electron from the photocatalytic mineral, from the UV light, is picked up by polyaromatic hydrocarbon embedded in the membrane, transferred into this protocell, and after a couple of steps of electron transfer, finally, the NAD plus gets reduced to NADH. So this is the schematic that we started out with. Does this all work? We basically did this reaction by UV radiation for 3 hours and looked at a bunch of different minerals, pyrite, greenockite. Uli, can you see the right side of my screen? I am seeing the participants on the right side of the screen rather than what's on the screen.
Yes, I see your screen well. I think this depends on where you position the window. If you move this window of participants to the top of your screen, you should be able to see everything better.
Let me see if I can get rid of this. I'm going to go back to. Just see. Yeah, here we go. All right, excellent. So yeah, you shine light for several hours. You start out at 0 hours. There's hardly any peak at NADH, which is 450 nanometers fluorescence, encapsulated within the vesicle. After 1 hour, 2 hours, 3 hours, you see that NADH is building up inside the peak. And this happens for sulfide minerals that were common on early Earth. Titania, a very widely distributed mineral. Zinc oxide, not so much, but zinc oxide and cadmium selenide were used as positive controls, not necessarily prebiotically relevant. How do we know that there are protons being generated outside the membrane? Well, we encapsulate pyranine within the membrane, and this is a pH-sensitive dye. So initially inside, the fluorescence of pyranine is corresponding to a pH of 8.5. That's at time T0. When we start the reaction after irradiation across a phospholipid membrane of this whole reaction, you can see that the pH hardly changes. So we don't really know what's going on. Are these protons being generated outside or not? Because we're measuring internal pH. However, when you have a fatty acid membrane, which is much more flip-floppy, it picks up, evidently, it picks up some protons from outside the membrane and flip-flops and bring them inside, and that's why the pH went inside, started to drop. And so these oleic acid membranes are actually being used to tell you, although it's an internal pH measurement, it's telling you that the protons were being generated outside and then being brought in. So basically, photocatalytic minerals of different kinds do promote transmembrane redox reaction, specifically of NAD plus to NADH, and do generate a transmembrane pH gradient. For comparison with the Bonfield paper, which Sharif's paper, which someone just mentioned, they do a similar thing using iron peptides clusters, but they'd get an inverse gradient where they create the protons inside and the OH hydroxide ions outside. So it's still a pH gradient and can still be used for chemical work, but it's the opposite of what is currently used in biochemistry. All right, but now, do these minerals and potentially divalent cations, which are also around in the environment, damage the membrane? So in 2017, we studied 12 different kinds of minerals, oxides, hydroxides, carbonates, sulfides, aluminosilicates, and looked at their stability as well as the rate of vesicle formation or protocell membrane formation in the presence of these different minerals. And so chemistry was varied. Size of the minerals was varied from micron-sized, such as the zinc oxide particles, to nanoparticles such as the titania, iron oxyhydroxide, goethite, as well as clay minerals, which you're seeing here edge on, and as flat nanoparticles here face on. These minerals have negative surface charge. These ones have positive surface charge. These are only 4 representative examples. We looked at 12 different minerals. You can see that they're all stable. This is a cryo-TEM image. And this was done in the presence of both decanoic acid at pH 7 and a decanoic acid decanol mixture at pH 8.5. We also did calcine leakage assays. You encapsulate calcine inside the vesicle, interact with the mineral, and check if the dye leaks out and the fluorescence changes. We don't see any of that. So the membranes are stable in contact with a wide variety of minerals. Now, do these minerals actually promote membrane formation? And indeed, we looked at here's the log rate in terms of a UV vis. As vesicles are forming in the presence of different minerals, you measure that as a UV absorbance. So we've got the rates here per second per meter square. And we found that all the minerals promote the rate compared to the no mineral control. This is not new information. Hanchik published this in 2007. However, they did not find any consistent trend with any mineral properties, whereas we showed that there's a clear trend with the isoelectric point, that is to say the surface charge of the mineral. Moreover, the micron-sized particles and the nanometer-sized particles fall on different trends. And you can see that beta titania, which is still a titania phase, so it is a chemically very similar to rutile titania, but particle sizes are different and crystal structure is different. Similarly, amorphous silica is similar to quartz, which is crystalline silica, but particle size is different, and also this is amorphous and this is crystalline. Even whole rock like komatiite and whole rock like tonalite, which represent primitive crust of the earth, follow these trends. So membrane formation rate depends on mineral isoelectric point. And during my PhD in 96, 97, I showed that the isoelectric point of minerals can be thermodynamically predicted based on the crystal structure of the mineral and the chemical composition. So we can then, you find me a mineral on any planet, and I can predict its isoelectric point based on its crystal chemistry and structure. And based on this correlation, I can tell you what the rate of fatty acid or mixed fatty acid alcohol membrane formation would be. All right, how about divalent cations? They were also present in the environment. So we looked at mixtures of oleic acid and phospholipid. You can see that this is the nominal ratio. So we have 10:1 molar ratio of oleic acid to phospholipid in the starting solution, and there's 0 magnesium chloride in the system. And we do measure within the membrane by HPLC. Indeed, there is a 10:1 ratio. We then add magnesium chloride to the system, and you can see that the OA ratio is actually decreasing quite drastically. And it's actually only 5:1 at magnesium chloride concentration of 5, and even lower at higher concentrations. Now, remember that the classical templated RNA polymerization by primers and whatnot requires 75 millimolar magnesium, which is out here. Now, we tested this again with HPLC. You collect the supernatant and the aggregates, and we determined that magnesium is basically binding to these oleic acid head groups and pulling them out of solution and making an aggregate and leaving a phospholipid enriched vesicle. And then we did this for different initial starting ratios, 5:1, 3:1, 1:1. You see this effect for all of them as magnesium increases, but the effect was most drastic for this 10:1 ratio. We're calling this the most primitive membrane because it has the maximum fatty acid and the minimum phospholipid. Calcium behaves in a similar manner. So if you have a pure fatty acid membrane, yes, magnesium and calcium are unhealthy for them. If you have a small amount of phospholipid, by pulling out the fatty acid and enriching it relatively in phospholipid, you're actually making a more robust membrane. So divalent cations acted as a selection pressure for promoting phospholipid enrichment and therefore stabilization of early protocell membranes. And then Jack Shostak's group published this a couple of months later, similar results. Finally, I'd like to get to the idea of minerals, metal ions, amino acids, and RNA. It has been known for several decades that Montmorillonite clay can react with an active RNA monomer and forms an oligomer of RNA so long as you have 75 millimolar magnesium in the system. What we did was, and this is the work of my postdoc Trishul Namani, when you add amino acids such as glycine, valine, alanine, leucine, glutamic acid, and aspartic acid, the reaction is promoted even further compared to the reference system, the classic Ferris system. If you add the basic and the polar amino acids, there's actually an inhibition of the reaction. And we have come up with a mechanism for this, which I don't have time to get into, but I'm happy to share with you later on. How do we know all this? Well, we've done both HPLC and multi-time of flight MS to confirm all of this, and several other control experiments to determine, different kinds of beta amino acids, blah, blah, to arrive at this, confirm this and obtain the mechanism. Interestingly, these amino acids are usually considered to be the prebiotically most abundant. These ones are either believed to be in low concentration. We did experiments where we added both of them, and then the effects will cancel each other out if you have them in exactly equally molar ratios. But if these are in smaller concentrations, then these guys still win out. Even more interestingly, we said, now let's look at a system where we don't have any magnesium at all. Okay, 0 magnesium, but we have glutamic acid and we have the mineral, and we find indeed we're still getting oligomerization. If you don't have any amino acid with 0 millimolar magnesium, you get nothing. You get a dimer, which is the same thing as the plain water system. In the plain water system also you get a dimer. You increase to 5 or 10 millimolar magnesium, you get slightly longer chain, 15 millimolar, slightly longer chain, 75 classical, 75 millimolar, even longer chain. So the original system, where there was no amino acid,
What are you making? Sausage and rice. I almost said don't make sausage and rice. I almost did.
mute their,
Somebody, could you mute yourself, please? Whoever is making sausage and rice.
But did you ever really tasty? Okay, if they're really tasty, then
Okay, thank you. We're done.
all right. So the reference system, the classic system, did not have amino acid, had 75 millimolar of magnesium, and you get about an 8-mer in that system. We're getting an 8-mer with 15 millimolar magnesium only. And this is when you have glutamic acid. Even if you don't have any magnesium, we're still doing better than the plain water system. So why is this important? It's important because now you can get polymerization in a wide range of environments where magnesium might be lower than this 75 millimolar. Also, these lower concentrations would have been compatible with the very old primitive membranes, which may have been only made up of fatty acids without even any phospholipid present. So indeed, I would say that we have made and are continuing to make progress in that direction. Many other groups are as well. And I would just like to acknowledge my research group. The work I presented today was mostly that of Poonam Dalai, some help from Puttu Usriana and Trishul Namani. Currently, I have a couple of more postdocs and students in the lab. For example, we're currently working out the mechanism for all this to work, which we have proposed, hypothesized in this paper, but now we're using MD simulations, and my postdoc Iskandar Arsano is working on that. I guess that is all I have to say. And thanks to funders, NSF, NASA, and a private donor.